In this lesson, we'll look at hypothesis testing with p-values. Now, it might seem a little complicated what we do here. I'll try to simplify it and break it down as much as possible, and it's really not that bad, but sometimes when you first hear it, it seems complicated. And I'll also show you a much faster way of actually doing this hypothesis testing, I believe, in the next lesson, and we'll use what's called rejection regions. But for now, we'll do p-values because you'll understand where the rejection regions come from, and also if you take a course like an upper level or graduate course and in a specific field, oftentimes they'll use p-values instead of rejection regions. Or if you use statistical software, a lot of the software that, if you take an MIT course or something, they would use software that gives you the p-values and they wouldn't go straight to the rejection region. So that's why even at the elementary level, we sort of introduce you to this. And it's really not that hard. It's just a picture. So let's start with the definition. A p-value, or a probability value, is the probability of obtaining a sample statistic, and I like to call it with a crazier value than the one from our sample. So what you do is you take a sample and then you say to yourself, self, what's the odds that I could have got a sample that was even crazier than this? And that is called the p-value. And in a picture, it's really easy to see. So here's a picture. If you look, you'll see there's a normal curve here. And it doesn't have to be normal, but we'll just go with that. And here's the claimed mu. So this is a claimed mu or a proportion. It could be a proportion also, whatever our claim is. That's the thing from our null hypothesis that we're trying to reject or fail to reject. And then here, our test. We took a test. And when I say it's a test, I put mu there, but you can think of it sort of like the test x bar, or it could be a p hat. That's what came from our test, which depending on which one we're doing, a p hat or whether we're doing means or proportions. So our mean is this dotted line, and our test mean is there. And then the p-value is this probability here. And what this is saying is, see, our test result is pretty close to the mu. And when I say crazier, I mean this stuff over here is crazier. It's like it's further away from the mean than our current test. What's the odds that we take a test, or probably we take a test to get something out here? And so that you can see that area under the curve is something we can get from a table lookup. And that's all the p-value really is. It's just grabbing, in this case, a left-tailed test. You see how it's the left tail of this picture. You can also have a right-tailed test. It could be crazier out here. Or you can have a two-tailed test where it would be like a donut on either side. So if you look at this A and B, I have two pictures here. Here's our x bar or p hat here, and our claimed mu or p here. And you can see there's the p-value here. Which of these is better for accepting the hypothesis? Like, which one of our tests here is better for the hypothesis? And you would say it has to be this guy, right? Because in A, this is A, and the B. In the picture in A, you see how our test was much closer, this distance. I'll call it D. And this here, this distance, see how this D down here is we were way away. And so this one was better for the mu, for the hypothesis. And then also, you remember, P is the area, or the p-value is the area to the left of the tested statistic in this one. So complete the sentence. A larger or smaller P is better for the claim. Well, if you look here, the top one has a larger P than this bottom one. More area, right? You take more tiles to cover it. And we said that this one's better for the claim. So a larger P is better for the claim. And that means if a larger P is better for the claim, then a smaller P makes us more likely to reject the hypothesis, right? Because it's worse. So it's worse for the hypothesis. We said this one's worse for the hypothesis, and this one was better for the hypothesis. And that above here was a left-tailed test. And there's also a right tail. There's no E on the end there. And a two-tailed test. So in science, and we put statistics in the sciences, at least according to Aristotle or Western philosophy, and the way they break up the world. In science, we like to measure things and have numbers. So we need a measure by which we can make our decision to reject or fail to reject the hypothesis. So we look at the probability of making errors. And we talked about these two things. We call it A, alpha, and beta. Now, We talked about type 1 error. That's that thing I called hunger to reject. Remember, type 1 is hunger to reject. So what that means is type 1 is when you reject, you falsely, I guess it's an error, you falsely reject a true hypothesis. You just don't know that you did it, usually. So alpha would be the maximum allowable probability of that error. And then beta would be the maximum allowable probability of type 2 error. Remember, type 2 error is where you fail to reject a false hypothesis. So you can control or make your decision on whether to accept or reject this hypothesis up here based on how much the probability of error is, or your tolerance. So alpha is the maximum allowable probability of type 1, and beta is the maximum allowable probability of type 2. Let's move on a little bit. So you usually focus on alpha, and that's for hunger to reject reasons, because that's the most common error to make. And our typical values for alpha would be maybe 10%, or 5%, or 1%. So often you'll see 0.1, 0.05, or 0.01. And what we'll do in order to make our decision is we'll compare the p-value to alpha, and that'll allow us to either fail to reject, or I'm calling it accept here with an asterisk, or reject the hypothesis. And remember, technically we never accept, we can only fail to reject. So the result of hypothesis test is either reject or fail to reject. And fail to reject is the same as observing that, like you do not disagree. If you've been in a meeting and you say, I do not disagree, that doesn't mean that you agree. It just means that you don't disagree. You're not sure. It's the agnostic position. So let's walk through an example and just see. Suppose we're testing a claim about the mean of a population. So it's about a mu. And we know sigma for the population. Our decision to reject or fail to reject will be based on the p-value in alpha. So we look at the p-value, the likelihood of a more extreme or crazier value than our sample, and the alpha, the likelihood we reject falsely. So let's say in this test, we allow an alpha of 5% or less. We say, okay, 5%. And we also determine the p-value to be 0.2356. What is our conclusion? So our p-value, here was the mu, and here was our x bar, and our p-value was 0.2356. And what we said was, right here is our alpha that, I'm going to say that's where the z sub alpha, I'll put it that. And that means under here is 0.05, right? Yeah. Maybe I wrote that wrong. Let me try that again. So right here is 0.05 is the z value that goes with 0.05. And that means that everything to the left of this value is 0.05, and it's less than this. So since 0.2356 is greater than 0.05, what that's saying is we're more likely to get a crazier p-value, or more likely to get a crazier sample mean than to make a type 1 error. So this says the p-value more likely is greater. The p-value is greater, so we're more likely to get a crazy sample than to make a type 1 error. So we'll fail to reject the hypothesis. But what if the p-value is 0.0236? Then you say, this one's greater, so we're more likely to make a type 1 error than to get a crazier sample than what we had. So our sample is actually quite reasonable. We're not likely to get a crazier one, or a sample was out there far enough. If you're more likely to have a type 1 error, then we reject the claim. If you're more likely to get a crazier value, you fail to reject. So, or if you don't like thinking through it all, then just say the p-value is bigger, fail to reject. The tolerance is larger, reject. And so let's just try a quick identify whether tests are left, right, or two-tailed. And so you can see here, if you have something like, oh, our mean, the null hypothesis is our mean is less than or equal to 5, then what you do is you find the alternative hypothesis, which we practiced last time, and it's just opposite, right? Mu is greater than 5. And here's a picture of that. And the alternative hypothesis always determines the test. So the alternative hypothesis is mu greater than 5, and you can see it's the right side, so that's a right-tailed. Now here's one, mu is less than or equal to 3. You might want to just pause it and write these in and then take a stab. So this one's going to be mu is greater than 3. So in our picture, we have 3, not 3, but everything greater than 3. Again, that's the right side, so we call it a right-tailed. And here, mu is greater than or equal to minus 4, so that means mu is less than minus 4. So in our little picture, we'd have minus 4, and everything less is the alternative hypothesis. This is HA. So that's a left tail. And then what's this one equal to? So mu is not equal to 17. So this one right here, if you find 17, we know it ain't that. It ain't 17, but it could be anything to the right, and it could be anything to the left for the alternative hypothesis. And that's two tails. That's a very common test. I will probably focus on that one a little bit. So let's try, when we do rejection regions, we'll focus on two-tailed tests. So given mu is 14, sigma is 2.1, and x is 10.5, let's find the z and the x and the area to the left of the z-tail. So if you have this, let's try converting to a z. Remember our little formula? So we have 10.5 minus 14 over 2.1. Little calculator exercise there. Oh yeah, remember this? Finding the z-score from like the first test. So 10.5 minus 14 is minus 3.5. Divide that by 2.1, we get minus 1.67. So on our picture, there's 0. This is a standard normal distribution because we're talking about z's, right? And so we find minus 1.67, it's to the left of 0. There's minus 1.67. And then what's the area to that? Well, if you want the area to that, it's just a table lookup of minus 1.67, right? Because that table gives us the area to the left. So minus 1.67, I'm just going to pop over here. See this picture? We want the area to the left. So minus 1.6, and then 7's way over here. It looks like 0.0475. So this would be 0.0475. So it says find the z and x. Well, the x is given. Find the z, we did that. And then the area to the left of the z for the left tail test. And you can see that's less than a 5% alpha. So in this case, we would, what do you think? If the alpha is greater, then if the alpha is greater, right here, we reject. So in this case, if it was a 5% alpha, we would reject. All right, so let's try this one. If z is 3.12, okay, so this has given us the z. What's the area in the right tail? So let's draw a little picture here. And 3.12 is there. And we want the right tail, so it's everything to the right. This goes down to 0, but never gets to 0, it's infinite. So 3.12, everything to the right of that. We'll just look over here and say, well, we want to look up 3.12, but we don't have anything to the right. So remember, we have those little rules. And when it's the right side, we do a 1 minus a table lookup. Right, because it's the probability z is greater than 3.12. This was the probability z is less than minus 1.67. Remember little rules. So this is 1 minus a table lookup of 3.12. So let's do a lookup. 3.1, the third column, 0.9991. So we got 0.0009. Not very likely. Now what if z is 2.41 and minus 2.41? So our picture here would be So we have minus 2.41 and 2.41. And this is a two tails, so it's going to look kind of like two tails, the left and the right side. Or I call that the donut a lot of times. So here, let's look at this one's easy, right? We just do a table lookup of minus 2.41. So that's easy. Minus 2.41 is 0.0080. 0.0080. And then this one we can look this up and then subtract it, but we should get the same, right? Because if you look at it, these are symmetrical tails about here. And so you could be 1 minus, look up a minus 2. Try that again. We did table lookup of minus 1 minus, we'd look up table of 2.41 here. And you'd end up with 0.0080. And they add them together, you get 0.0160. And then that's the area for both tails. So if you have a two-tailed test, you can just take one of the left value, look it up, and times 2. That's the bottom line for that. And then something we use for actually testing is this thing called the standardized test statistic. And what this is doing is it's taking the difference between our sample mean and the hypothesis mean, and then dividing it into what we call central limit theorem sigmas. So I'm not going to get into that, but that's just what we use for a formula. So it'll be x bar minus mu. I might want to write it just to get it, over this special sigma. That's what we call the sigma x bar from the central limit theorem. Remember that? Okay, so let's try a little problem here. The claim service time is 13 minutes or less. Before I get that, this is got a skeleton on the next page. So the claim service time is 13 minutes or less. So a random sample of 32 secret shoppers has a mean, and we're going to assume that we know sigma is 0.19. And if we want to keep alpha at 1%, should we reject or fail to reject the claim? So let's see what we need to do on this next page. The skeleton says identify the null and alternative hypothesis. So right here, the claim is our service time is 13 minutes or less. So that's going to be an average service time. So the claim is that, I should put a colon there, mu is either 13 minutes or less. That's the claim. So the alternative we can figure out and say, oh, the alternative is just that it's greater than 13. So right there we know, if we draw that, 13, from the alternative hypothesis, which is that thing's greater than 13, that it's a right-tailed test. Now we can calculate the z, so we need the x bar minus mu. So we have x bar, or from our sample, we had 12.9. So 12.9. And the mu is 13, right there. Over the sigma, I forgot what that was already. Sigma was 0.19, and we had 32 shoppers. So, already forgotten that was a 0.19? 0.19 and 32 shoppers, okay. 0.19, and we had 32 shoppers, so square root of 32 in there. And then figure that out. It's minus 0.1 over 0.19 over square root of 32. So I'll just take another step. Minus 0.1 over, let's take that out. We have 0.19 divided by the square root of 32 is 0.03359. This should be enough. So we have negative 1 divided by 0.03359. Negative, do I believe that? I don't believe that. 0.1 divided by 0.03359. No, still don't believe it. Okay, 0.1 divided by 0.03359. There you go, 2.97. So minus 2.97. Now that I was able to hit the correct buttons on the calculator, we have minus 2.97 as our z value. So we have a right-tailed test, right? And our z value is minus 2.97. So we're interested in everything to the right of that, which is a lot. So our p-value is 1 minus a table lookup of the z. other words, we're interested in the probability that z is greater than minus 2.97. That's our p, our probability. So 1 minus, we do a table lookup of minus 2.97, minus 2.9, and 7's way over there, 0.0015, 0.0015, and so we end up with 0.9985. Yes. Okay. Now we consider p versus alpha. What was alpha? Alpha was it 1% or 5%? We just have to look. Alpha was 0.01. It was 1%. It is 0.01. So if we consider the p is 0.9985, and we consider the alpha 0.01, there's alpha, and the p, which one's larger? Would you rather have 99 cents or 1 cent? And you say, oh, that one's larger. Obviously, p's larger. So if p is larger, then we fail to reject. Pretty easy, right? And that means that we're more likely to get a crazier value than we got in our sample than to have made a type 1 error. So let's try another one here. So claim cost of a Ford Mustang is $21,500. I think they're more than that now. A sample of 25 purchases shows this amount, and then we'll assume a sigma, and the population is normally distributed. Since n is less than 30, we have to assume that. Is there enough evidence to support the claim with the 5% alpha? Well, let's try the alpha. So again, we're talking about the claim cost of a Mustang, and this is talking about the average. So this should be a colon here. We're saying it's 21,500. And there's no less than or greater than, so we're going to do equals. And that means our alternative says not equal to 21,500. So if we draw that in a picture, there's our 21,500. It means it could be anything to the right of that, or the alternative hypothesis, or anything to the left. We call that a two-tailed test. And so let's calculate our z-value using the normalized test statistic, and we can do that because we assume a normal distribution on the population, or if you had 30 or more in your hand, you could also do it. This is using the essential limit theorem hidden behind all this. So z is x bar minus mu over sigma over squared n. Let's put those in. The mean from our sample was 2695, and our claim was 21,500, and the sigma was let's see here, 2250. And how many did we have? We had 25 purchases. Square root of 25. Nice even square. So if we calculate that up, 2695 minus 21,500 is wow. Minus 805 over then 2250 divided by, this is 5, isn't it? 450. So it's 805 divided by 450, or minus 1.79. So now we have a z. We're saying, in this case, here's our 0, and it's a two-tailed test, and we're interested in minus 1.79, but we'll also be interested in its sister up here, its identical sister 1.79. So we've got both sides. So our p-value here, we'll just do, we want the probability that z is less than minus 1.79 plus the probability that z is greater than positive 1.79. And we showed on that last problem, if you can't remember that, we could just do 2 times the probability of z is less than minus 1. In other words, this area here is the same as this area here. So we'll just look this one up. That means we just do 2 times a table lookup of 1.79. So 2 times, let's look that up. I'm sorry, minus 1.79. Look up minus 1.79 here. Minus 1.79 is way over to the end. 0.0367. 0.0367, and then times 2. 0.0367 times 2. 0.0734. 0.0734. So our p-value is 0.0734, about 7%, and our alpha in this case was 0.05. So who's larger? If you look here, you say, well, I'd rather have 7 cents than 5 cents. So that's p is larger. Remember, up here, if p is larger, we fail to reject. So this is another one we fail to reject. So we say, well, you know what? Our that little 21500 R sample was close enough to that. And if you think about it, that's about right. About $500 off. That's really not that. Well, maybe $1,000. That's not that far off. And if you consider 5% of it, 5% PN. Well, what is 5%? 21,000. About $1,000. So it's kind of close, but it's not there. All right. And that is a powerful tool. I mean, if you think about it, that's a really good way to look at things. We'll get to rejection regions next, which is a little easier to think about, but this is how a lot of scientists do their work. All right, that's the end of the lesson.